Just thought I would add some humor to that. Okay, so nuclear chemistry. All right, little history. One of the pieces of evidence for the facts that atoms are made, basically she just helped discover nuclear chemistry was Madame Curie. You've heard of her. Okay. She also actually died from that. She died from radiation poisoning because they didn't know that was a thing. So she actually also discovered radiation poisoning. Not the best thing, not the best thing to discover, but she did. Okay. Isotopes. Remember, we just talked about isotopes. What are isotopes?
The protons are the same. The neutrons are different.
Correct. Protons are the same. That same atom. They have different number of neutrons, and so that gives them different mass numbers. Okay. And here's 3 naturally occurring isotopes of uranium are 234, 235, and 238. Remember, those are the mass numbers. And what is your mass number?
Proton plus neutron.
Protons plus neutrons. That's why we do this unit now, right afterwards, because we just did it. I'm going to keep you all awake today. Okay, the nucleus. Okay, the atomic nucleus is made up of protons and neutrons, which are collectively we call nucleons. Okay, when we're talking about for some reason, in nuclear chemistry, they call it nucleon. They have a different word for it, but it's basically the nucleus. Okay? A nuclide in nuclear chemistry is the atom. So if we said I had a nuclide of uranium-234, it's just a different word. These are also some of your definitions. Nuclides can be represented in 2 ways. Remember, you can represent them like radium-228, like we just showed, or you can do the little symbol like that. And remember, mass number is the number of protons and neutrons. And atomic number is a number of protons. Okay? So if we wanted to know this particular one that they're showing, which is radium, if we wanted to know how many neutrons, so we want to know neutrons, how would we calculate that?
Mass number minus protons.
Mass number minus protons, which would give us how many? 140 neutrons? And that's basically a review from what we just took a test over. Okay, and of course, atomic number is the number of protons, and if it's a neutral atom, also the number of electrons. Okay, only if it's a neutral atom, though. Okay. Nuclear reactions produce physical or chemical changes. What do you think? Is it a new substance? Is the reactant the same? Does it follow the law of conservation of mass? All these questions, and the answer is yes to all of it, except for the law of conservation of mass. Okay. It doesn't strictly obey the law of conservation of mass. And that is because we are messing around with the nucleus. Okay? All other chemical reactions that we have are only dealing with the electrons. Electrons are being transferred or shared. But in a nuclear reaction, we are changing the nucleus. So we have to balance them a little bit differently. Okay? Which is what your homework is on today. And we are going to take a homework quiz over that tomorrow. Okay, so just like when you know there's a homework quiz, you can do a couple of them, you can do all of them. Get to practice. Okay, they're quick and easy. I would do all of them just so you make sure they're all covered, but we will have a homework quiz over your homework today. If you look at this reaction, the way that you balance it, okay, is the number on the top, they have to add up on both sides. They have to be the same. Okay, number on the bottom has to be the same on both sides. So on this side it's 92, right here. Over here it's 90 plus 2, so that equals 92. Okay, so they add up to be the same number on top. Okay, so let's practice those in a second. Classic chemical changes, of course, we said involved with the electrons. We are changing the nucleus. They're not really either physical or chemical, they're nuclear. It's like a different category. And they have a lot of energy. Okay, a lot of energy. The release or we already said this. To be clear, the mass is not necessarily conserved, but the particles are. So we're conserving the particles. Basically, what's happened is some of the mass is being converted into energy. Okay. Told you I'm gonna keep you awake. Mass defect and nuclear stability. Stability. I'm making up words. Okay. So if we look at the actual mass of what a helium atom should look like, we know it has 2 protons. How many electrons does it have?
2.
Okay, and it also has 2 neutrons. Okay, for helium-4 because it's got a mass number of 4. If we add all that up, we should get a total mass of 4.03 and some change. Okay, look at my periodic table. What is the actual mass of a helium atom? Average atomic mass.
4.00260.
Okay, the actual mass is 4.00260. Okay, so that's a difference of 0.03 AMU, and it's called the mass defect. Okay, and that's basically the amount of energy that was converted. I mean, the amount of mass that was converted into energy. So when we're talking about a helium atom, basically this amount of mass was converted to energy. So that's where that difference comes from. Okay, and it's every nuclide has a mass defect. Okay. The mass defect is caused by the conversion of the mass to the energy when the nucleus was originally formed. And I will leave that theory of when it was originally and how it was originally formed up to you. Okay? Using Einstein's equation, E equals mc squared, we've heard of that. It's like famous, right? Well, we can actually calculate the energy that was formed when the nucleus was formed. This is called its nuclear binding energy, which is one of your definitions. Okay? Nuclear binding energy, which is also one of your blanks, right? Okay? It can also be thought of as the amount of energy required to break apart a nucleus. So if we're trying to do a nuclear fission reaction where we break them apart, that would tell us how much energy could be released. This is fun. All right, nuclear reactions. Okay, in nuclear reactions, we're going to involve the protons, neutrons, and electrons of a single atom. So here we have, this is how we symbolize a proton. Okay? Remember mass number, atomic number. So that makes sense that it's 1 and 1, right? Electron is going to be symbolized like this. A negative 1 on the bottom because it doesn't have an atomic number. And then 0 because it does not contribute to the mass number. Sometimes if it's beta, we'll do that funny looking B. Okay? And this is just to show you how we're going to write these. And then a neutron is 1 with a 0 on the bottom because there aren't any protons. Okay? And we'll need these symbols to help balance these. Okay? I forgot the sound was in there. I need to take it out. Okay, so in nuclear equations, remember we have to have the top and the bottom add up to each other. Okay? So if we look at, let me go ahead and get the rest of that on there. Okay? If we look at this particular one where we have a beryllium plus helium and we turn it into carbon and a neutron. Okay? If you can't get your nuclear equation to balance, sometimes we have to throw a neutron in there, and that's because this reaction released a neutron. Okay? So we add up to 13 on the mass number on both sides, so we're good. And we add up to 6 on the atomic number, so we're good. Okay? This is also called transmutation reaction. Okay? Because beryllium-9 became carbon-12. That is a transmutation. Okay? It's becoming something else. Makes sense? We're mutating, right? Okay? Also one of your words. Okay, practice. We're going to practice just balancing some equations. You have these in your notes. Okay, so what would we need here to balance this out? The best way to do this is not try to figure out what the symbol is until you're done. Okay, so if this is 84 right here, on the other side I have a 2. What plus 2 will equal 84?
82.
82. Okay? Can y'all see that, or y'all need a different color? Is that better, though? Okay, 82. Now, on the top, what plus 4 will equal 218? 214. Okay? Now, we identify elements with their what?
Atomic number.
Atomic number. Okay, look at the chart and tell me what element is 82. Lead. So we have lead. Okay? PB. So now this is balanced. Okay? So now this is balanced. So let's do another one. In this one, I have 99 on this side. Sometimes it helps to draw yourself a line so you know where it's at. On the other side, I have 99 plus 2, which is how much? 101. And then I have 253 plus 4, which is 257. So I need this side over here to be 101. 1 plus 0 is 101. 101. Okay? It wasn't a trick question. I was being silly. What plus 1 is 257? 256. So find element 101, and it is MD. And now that's balanced. Okay? Seem okay?
On ours.
Do y'all have a different example?
We just have it.
You have this and not that? Okay, well,
We're just
yeah, I don't know why that happened. On your notes it's different. That's weird. Is this the same one on your notes too?
Yes.
Okay. So on this, that's the same one we just did. There we go. It took a minute. Do y'all have this one? And is it like this? Okay. So we've been doing the ones on the product side. Now we're going to do one on the reactant side. Okay. So I have 60 and I have 61. Okay. What plus 61 is going to be 60? Negative 1. And then that's the same. And what symbol is a negative 1 with a 0 on top? Electron. Okay? So if it's not an actual symbol on the periodic table, you're going to put either proton, neutron, or electron. So pretty straightforward. Okay, so now we're going to do the types of decay. Oh, just put it in that folder because that's where they are. Yeah, I haven't graded them yet. All right, so here we have a radioactive atom. We have energy being released in a particle because when a nuclear reaction happens, we're releasing energy and usually a particle. Okay. You know what? That's annoying. I'm gonna mute my computer.
Lesson ended for today.
No, I can't do it without turning it off and starting over, and I'm recording, so it's not gonna work. You're just gonna have to listen to the noise.
Can we turn down the
Yes, get the thing and you can turn it down.
Go great.
Okay, radioactive decay is the spontaneous disintegration of a nucleus into a slightly lighter nucleus accompanied by types of emission. These are the types of radioactive decay. The first one is alpha emission. Okay, alpha emission is basically we're emitting a helium particle. Okay, so it looks like this. Okay. At the bottom it says blank will shield you from alpha particles, paper, or clothing. They're very weak. So paper or clothing will shield you from alpha particles. So they will keep you from being affected by them. Okay? So this is the alpha particle. Sometimes you'll see it like this. That's supposed to be one of those funny looking A's, but I'm not very good at drawing it. That means the same thing. So sometimes I don't know if it shows up as an alpha on your worksheet. Normally we write it as helium, but you do need to be aware that an alpha particle is basically a helium nuclide. Okay? Oh, sorry on that. That helped. Good job, Craig. Beta emission is when a beta particle is basically an electron being emitted from the nucleus. Okay? And it's converted to a proton, so it's going to change the mass. Okay, so it looks like that. Or, here's one with actual elements. Okay. So you can, remember you can see this like this, or you could see it like this. Either one is sufficient, because basically a beta particle is an electron. So either way is correct. Okay. For that one, metal foil will shield you from, actually it should be lead. Lead, yeah. Lead will shield you from beta particles. Okay? The next one is a positron emission, and it's basically a backwards beta. So in a beta it was emitted, right? In a positron it's added to it. So it basically a proton is converted into a neutron, and it looks like this. It's a pos. Oh no, it's electron capture. I said the wrong one. I'm sorry. Positron is a positive electron. Okay, positron is a positive electron. So same concept. I could also show it like this again. I could say E01 for positive. It's a positive electron, which seems weird, but it is. Okay, so same kind of shielding for that, because it's the same amount of energy present. Then there is, electron capture. It's left out of my notes, but it's in yours. Okay. So again, electron capture is when an electron is captured. So it would look like the 106 and 47 silver. It captures an electron or a beta particle, either one. So then you would have 106, 46, and then that is palladium. Okay? So electron capture is basically the electron is on the reactant side. Beta is the electrons on the product side, and then positron is a positive electron. Those are the three that kids get confused on, because the alpha is all by itself. It looks different, but those you got to put them in your mind correctly. Okay. And then gamma emissions, you'll notice that there's no reactions with them. Gamma are the electromagnetic waves, or the electromagnetic high energy waves that are emitted during these. They are very dangerous. They're the highest of the electromagnetic waves. And you need lead or concrete to protect you from those, like 6 foot lead or concrete. And write that down, 6 foot. When you're looking at a nuclear power plant, have you ever you've seen one on TV and you see those big, huge domes? Right? Those big, huge concrete domes. Every nuclear plant has them. That's where the reactor is in there. And they're usually about 12 foot of concrete, and that's to shield any stray radiation from escaping. 6 foot is what's required, but they do double that. Okay. So one thing you do need to know, and I don't know if it's on the next page. Not yet, but I want you to write this down somewhere, and that is this. Okay. Because this is going to be important. Weakest of the energy is alpha, and highest energy, meaning the most detrimental to you, is the gamma. Which, if you didn't get that from what I said it took to shield you, I want to make sure you know it. Okay, so they're the weakest. Alpha only takes paper or clothing, and the highest is gamma. Gamma are the ones that, if you're exposed to too many of them, they can kill you or cause major illness with radiation poisoning. So, when we watched the video on Friday for Chernobyl, and it said those people were basically burning from the inside out from the exposure, that's because it was gamma radiation. And some people died instantly because it was such a high, the people that were closest to the reactor when it blew, and that was because they got such a high dose of it. Okay? All right. So here's a picture of gamma radiation. The parent nucleus and the daughter nucleus. I believe that's some of your vocab. The parent nucleus is always bigger. Okay? It's like your parent's always older than you. Your parent nucleus is always bigger. The daughter is what comes after. Okay? You can't have a daughter before you can have a parent. You gotta have a parent and then a daughter. Okay? So if they talk about the daughter nuclei, that's what it decays into. Okay? So here's those pictures of showing you what it takes to shield them. Of course, gamma is the worst. And then we're going to complete these nuclear reactions. And then I'm going to walk around and help you with your homework. Okay. So what do we need to fill in the blank here? You don't have this one?
No.
Okay, well then let's just do it together verbally. So I have 96 over here and I have 94.
You need a helium.
I need a helium. Come back to the white. So that completes it. And what kind of would this be?
Alpha.
Alpha. Okay. Let's do another one. How about this one?
Beta.
You need a beta.
Different.
Do you want to do the E or the B?
B.
Okay, so this would be a beta. Okay, so on your homework today, you're going to balance those, and then you're going to tell me what kind of emission is it, or kind of decay is it? Is it alpha, beta, positron, or electron capture? There will not be any gamma, so don't write gamma, unless there's no change. Sometimes if it stays the same, and you see this funny looking particle like that, that's a gamma. And so sometimes they may show you one that looks the same, like the mass number and the atomic numbers are the same, and it's a gamma. Okay? And let's do one last one, and that's where we'll stop. So what do I need to put in the atomic number position? 0.
Oh, atomic number 1.
1. And what do I need to put on the top?
0.
0, which makes this what kind? It's a positron, positive electron. Okay? Are we good for practicing? Okay, that's where I'm going to end then.